some amazing little planes, and his mom was there. And your older brother that first time.
Yeah.
And she had driven you. And I'm sitting up in the bleachers watching him fly his plane, and his mom is going, "Man, all Ben wants to do is build these little planes. And his brother's off at college, and he doesn't seem to care about school and whatever." And so then he goes off to Penn State, gets an undergraduate degree in aerospace. Then he does a master's. He's doing summer internships with Matt. And the last time I saw you was right before you moved to California. And I said,
"Oh, really?
Please tell your mom that it's all worked out."
That's great.
Yeah,
15 years ago.
That was those were good times. So we're going to talk about the Mars helicopter. We were going to use the monitor, but I think my printouts are bigger, so we'll just use these.
Yeah.
So the NASA Mars helicopter was a concept. I guess it's been an idea for ages. I just found out last night that Copter was approached 2005 to potentially help, start working on the fundamental pieces. But Ben and I have been working on an actual Mars helicopter that's going to launch next year in July, and then land on Mars in 2021. It's been a huge effort. I'm the chief engineer on AeroVironment's part of the rotor system work, but I'm kind of like more of a project manager and system engineer. Ben is the lead engineer, lead designer on the team, so he and I have put in the most time out of the about 20 people at AeroVironment that have worked on it. And we all have our initials on a certain part deep inside the helicopter that's going to Mars. So let's see, I think that's it. So there's different ways to do missions on Mars. You can have something orbiting, or no, a flyby, which you get just an image as you're flying by. Depending on what the weather is, you might get something interesting or not. You can have orbiting satellites, which you get the view straight down. Again, you're limited what you can see. You can have a lander, which you get the close-up views, but it's stuck in one spot. Obviously, you can do rovers. So after the first little rover that only went like 1 meter, they decided that was a good idea, and they made more sophisticated rovers. So it's been kind of going through this evolution of doing more and more elaborate missions. And then most recently, the idea of doing a helicopter, and this is actually the CAD model that was done by AeroVironment with JPL's inputs at the very beginning. And the interesting part is that looks pretty similar to the actual one. This isn't actually it, but this is the actual one here. So it's kind of cool that it stayed that close. So problem with operating on Mars. The air density is a big issue. So on Mars, a cubic foot of air at sea level on Mars is, I think, weighs as much as this Post-it. A cubic foot of air on the surface of Mars. Now, a cubic foot of air in this tent right now weighs as much as a AA battery. So that's kind of significant. The AA battery, that's what we're flying in. We make something that's being buoyed by a cubic foot of air. So at 120,000 feet altitude on Earth, it's basically the same as the surface of Mars as far as air density and the difficulty to fly. So wings have to move 10 times faster to deal with the 100th air density. And not many planes have operated at 120,000 feet without rockets, but there have been a couple. An F-104, the NF-104A had a rocket boost to get going, but it managed to get up to 120,000 feet. And then a MiG-25 actually got up there just, I think, on its own power. And then you'll say, well, what about SR-71, U-2? SR-71, what they published, 85,000 feet, U-2, 70,000 feet. But there's one weirdo plane that looks just like a joke right here, and that's AeroVironment Helios, so that's the same company we work for. That got up to 96,800 feet a few years back, solar power with electric motors. So that one really clawed its way up. But that one is the closest to our helicopter. It's electric power, it's very lightweight, it's delicate. The rotor blades are actually designed with the same design code as the rotor blades for the Mars helicopter.
Matt, what's the gravity on Mars?
The next slide. What planet is this? What planet is this? Which one is more mass? Big boy. So the gravity on Mars is a little over 1/3. It's more than the. It's kind of on, sort of like the moon. It's a little bit more than the moon, but it's way less than Earth. And back to my batteries. If you held a AA battery on Mars, just like this, it would feel like a AAA battery on Earth.
Okay.
So you get that much more weight you can lift. So you've got a gain with the gravity, but you got a loss with the air density. So which one wins? And I was just asking Ben a couple days ago. It's not absolutely a simple answer, but the general answer is the air density wins. You lose on Mars. It's harder to fly on Mars. And that's only one thing that makes it harder to fly on Mars. So I started on the project in about 2013. I was brought in because another lead engineer wanted to get off the project. We initially used hobby parts to make a 3-bladed rotor system, just using a swashblade drive system from a model helicopter. We made our own blades using an airfoil that we selected, and changed the collective pitch and ran this up in a small test chamber at JPL to get it down to that super low density. And it's also CO2. So it's not nitrogen, oxygen, it's CO2. So the Mach number is a little bit different. So, and that's worse than Earth, right?
Yeah.
So you have to worry about getting Mach tip drag sooner than you would on Earth. So I didn't work on this, but this is where I came in, making this little, it's kind of a PR stunt. It's got a brushless outrunner motor from one of our AeroVironment drones. It's got a 4-bladed rotor. All those 4 blades go the same way. It kind of looks like it's a coax kind of rotating, but it's not. They just go in. And it was what I could do with a small budget. And this was set up, this is just a mock-up little body on a little crossbar and guides, and it just went up and down a rail in the chamber at the Mars atmosphere. And they wanted to just get some demos so they could get like whatever it was, $50 million. I don't know how much the entire Mars helicopter project funding from NASA was. It's tens of millions.
It turned out to be around
30. So they needed to convince management you can fly on Mars, it's viable. But every time we did a test, they said that's not enough to convince upper management. So this is the point where Ben came online, because we had to make, I said, well shoot, we can make some little model. We didn't have to make it full size, make a little one. I'll fly it in the chamber. We're gonna fly it around. It's easy. Ben's like, what? So we took an MX, the E-Flight MX2, MCX, look, the little coax. MCX.
Yeah.
And then we took the motors off, changed the gearing, put much bigger motors with heat sinks, and then made some custom rotor blades. And I'm going to pass those around now. Let me just start by showing. So these are super lightweight. So Ben developed this technique of making these very lightweight rotor blades, carbon fiber skin. Well, say what you did.
This was actually a wet layup. I'll pass these around. It's a spread toe carbon fiber skin over a foam core. These are molded in hard
Pass
jelly.
them all around? Or do you want to
Yeah,
talk
these
to
are-
any of them? So you can see
No,
the
we'll pass them
MCX
all around.
hook connection on this one.
Yeah.
You can see we use the actual E-Flight little hub just scabbed onto it. So yeah, pass this around. So made some beautiful rotor blades, and we thought we could fly this in the chamber just with simple RC, and we had to have tethered power because they didn't want lithium polymer batteries in there at that point. So we made 2 helicopters. this one is at JPL. This is the one that was based on the Hobby Coax. Then we made this one, which has an E-Flight Park 180 brushless motor over here, direct driving 2 bevel gears, so you get the counter rotating just with the single set of gears, and it's hardly geared down. It's like 3 to 1, 2 to 1, so it's almost like direct drive. So this can spin up extremely fast, and it's also very unpleasant in Earth atmosphere because you're throttling way down and trying to maintain height. And this one uses the flybar stabilization system on both rotors, and we didn't do the analysis to figure out if that would work at 10 times RPM, and it turns out it doesn't. You want to say anything before we show the video?
Matt, do you have thermal problems?
Well, we had to put heat sinks on this motor was okay, it got warm, but the small brush motors that we put on the other one, I had to put corrugated black aluminum radiating heat sinks because, yeah, they got hot because we didn't have the time to make anything matched and efficient. And although these are light because they're not carrying batteries, they are lifting the wire, which is rather significant.
Yeah, this whole effort was around a month and a half from when we kind of started designing to flying over at JPL.
And you can't just put anything in the chamber. They won't let you put most types of tapes, most types of glues. Anything that has an odor can't go in the chamber. I remember I was like just carrying the regular roll of masking tape, tan masking tape, like through the door because I just needed to do something. It's like, stop! What? Masking tape? No masking tape. Capped on tape.
Yeah, the chamber Matt's talking about is JPL's space simulator chamber. So it's a national asset, I think is what they call it. It's what NASA uses to test most of their satellites in a vacuum. So it's a 25 by 80 foot.
Even in the small one, though, I got dinged for the 10 foot, the one they call the dirty chamber.
Yeah.
They're really particular. So what happens is, and when you pump it down to a vacuum, all the molecules that normally going into your nose when you smell something, they're just going everywhere and sticking to anything. And some of these chambers have windows and lenses and lights to simulate the sun. And you can't have oil sticking on those because it screws up the optics, and then it's actually dangerous. So they're very particular. And they have all kinds of horror stories about people that have snuck stuff in there and then it exploded and the whole chamber. Can you imagine like 100 foot tall, 25 foot diameter, crazy chamber, and it's all contaminated, all the surfaces are contaminated. And it's not just smooth, it's all these crazy radiator fins because they have to be able to pump liquid nitrogen through the walls to make it as cold as space.
How would you deal with the dust on Mars?
They basically told us do some really simple tests and don't worry about it. It's like talcum powder. It's very soft. It's not to the point where it's going to cause your bearings to like grind, but if you pack it in, it'll just block it. So we did a fair amount of tests. We do have dust seals. We're not going to go into that level of detail. We can talk about it after. I mean, you might touch
Yeah, I'll
on
talk
it
about it a little bit. Most of the bearings are at least shielded.
Yeah.
Yeah, there's felt seals on most of them.
So the belt seals, but like if there's dust buildup on the blades,
Yeah.
they're going to go out of balance, and hopefully it sheds off because it can't tolerate much out of balance. So let's try and run these videos on your screen.
Sure.
Is
This is going to be hard to see.
is it pointless?
The front row might be able to see it. Can you guys? Can you see anything?
Maybe tilt it down.
We're going to see.
So basically what happened with these little models is they weren't stable, and all I could do was just kind of throttle up and just kind of
So this one's Earth atmosphere. You can see I'm standing right there.
So they're trying to video, I don't know.
Oh, sorry.
But even in Earth atmosphere, they didn't fly very well.
Yeah. So this is in a
But
vacuum.
in the Mars atmosphere, they did get off the ground, and there was no question that they had enough thrust to fly, and that was really the goal. And I was really feeling bad because we failed, because I told them this is going to work, because I had done the toy helicopters, like Petter, and it's like we know how to do this in our sleep. We can put these things together, but with the 10 times rotor speed, it's just not the same. The rotors just become these massive, strong flywheels, gyroscopes, and and the aerodynamic forces are really low, so it's the kinetic forces that are dominating. So, and we didn't manage that. So, but it turned out to be good because the JPL helicopter team wanted to show that it was hard to control a helicopter on Mars, and it's going to be a big effort, and we need lots of money.
Give us more money.
So JPL did all of the avionics, the batteries, the IMUs, the cameras, the navigation system, obviously the ground station on the rover, and they managed the deployment system that was built by another vendor. So what we did was kind of the structure, and Ben is going to speak to that, what the parts that we did. Yeah, I was going to talk about temperature a little bit. So the temperature range, minus 130 degrees Fahrenheit to plus 68. So we have to deal with the batteries freezing overnight. So there's a solar array on the top of the helicopter that charges. So we kind of like fly one day, and you spend all the rest of that day and the next day charging the batteries, because the batteries have to run heaters to heat themselves.
Oh, jeez.
Yeah, and some of the avionics is particularly delicate. Our stuff doesn't get heated, so we've got circuit boards up in the motors, the brushless direct drive motors. We've got circuit boards there and in the servos, and those just get down to minus 130 F every night.
Wow.
And so the circuit boards are made out of special material. They're not fiberglass, they're not regular epoxy. It's all the stuff and the coatings and yada 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 and yada yada yada. Lots of money and lots of time, lots of testing, lots of getting yelled at by JPL. You can't use that material. Radiation is a problem. I can't really speak to the radiation too much. It's much worse on Mars than it is on Earth. You don't want to live on Mars. If anybody tells you they want to live on Mars, they haven't done their research. It's 3 times more radiation than the space station. So you have to live underground. You have to live under dirt. You got to live under yards of dirt. It's the only way. And go out once in a while and play your long distance football. Go ahead. Throw your football like 10 miles. Good. But the radiation is gonna eat you. Like the astronaut that spent a year in space, he had a lot of health problems, and it's 3 times worse on Mars, and you're going to be stuck there. So the electronics get flipped bits, MOSFETs that are being held off, like to turn on. We use pretty much consumer electronics that just went through testing and sorting, and there's some probability that it's going to get damaged either in cruise on the flight from Earth to Mars, or when it's on the surface. They have features of being able to reset and restart, and the navigation computer doesn't have to work. It can fly just on the IMU if necessary. But radiation is a problem. Okay. And then get into the next developmental demonstrator. Was a 1-to-1 size. So this is about 42-inch diameter. And it has coaxial counter-rotating rotors. This has cyclic and collective on the lower rotor, and only collective on the top rotor for yaw. And this was one of the configurations we thought the final copter might have, but it isn't. And this used New Motors brushless in-runner with lots of gears. It had a very circuitous gear path. And this was the last thing that I kind of had a lot of influence in designing, and it went over to Ben. But this was kind of my last one that I worked a lot on as far as like the overall design. But Ben was already doing all the detail work on all the carbon fiber parts, especially the blades. But this flew, and this had tethered power, and it used a Vicon system, that motion control capture with all the cameras, like they do at Avatar. So that was used to get the exact state, the angles and the speeds and the positions of the copter, because the chamber, although it's 25 feet across, it's got stuff inboard of that, plus there's the structure for the Vicon. So it only got, what is it, like 15 feet across?
About, yeah.
So we're flying a 42-inch copter without eyes on it in about, 15 feet of circular space. That's got a tether, which the tether wants to make it go off.
And
so
this was the first fully autonomous one.
And so, so no pilot in the loop. And it had, this one, did it have a gravity offset? No, this had a safety capture. So I was kind of a pilot. I had a RC box and a seat of prominence at the flight test table. And my job was to, if it started going bonkers, I'd hit a throttle and it would throttle up a winch way up high that would pull a Spectre string, and it would pull the helicopter up, and it had a tether on the bottom. So if it was kind of going over here, you'd pull it, and it would kind of go whoop. You know, it would save it. Fortunately, we never had to do that, but there were all kinds of things I had to be careful when I did that, and so that was interesting. So let's do this little demo here, because we've been talking about how bad the subscale flew, and you're going to see a really bad flight here. I don't know that it could be any worse than if it was in still air. So just kind of be ready to catch it. Well, what's going to happen is as soon as it takes off, wherever the wire is, it's going to pull it, and it's going to go the opposite direction. So I don't know if you want to like do anything. Run the other way.
Do you want it on the ground, or do you want it?
I don't know. This is going to be awful. Let's just do it. So I've got throttle control, and then I've got collective pitch on the bottom so I can rotate it, but it's going to be bad. So you can see, because the wire's way under the center of gravity, it just goes off. But I don't know if I can throttle this up full. No, I limited the throttle step.
Oh, okay.
But when this thing is wound up in the chamber, it was like.
Oh, yeah.
Yeah.
It's like 7,500 RPM.
Yeah, it was crazy. Wow. We'll do it one more time. See if we can get a good crash for you guys. Yay! That's what we were looking for. That's what we were looking for. All right, let me hand it over to Ben for a bunch of stuff, and then I'll talk a little at the end.
All right. I'll apologize in advance. I've got a cold, so if I start hacking up my lung, that'll take care.
He'll probably talk to that, the Mach number of the real one.
Yeah, we designed it to stay below about 0.75 on Mars, right? And so on Mars, Mach speed of sound is about 20% lower than it is on Earth. It's 240 meters per second. So that was just a design point, right? We didn't want to deal with Mach divergence at the tips.
Do you design special airfoils for very low Reynolds numbers
Yes.
and high Mach numbers?
Well, very low Reynolds number was kind of the driving point, right? You want it to be very thin for both very low Reynolds number and very high Mach number.
Where's Gordon? Where's your 12% camber?
Boy. Yes, there were special airfoils. I'll show you this.
All right.
Okay, so let's see. So I guess I'm going over mostly the flight implementation, or what we call the flight implementation. So this is moving more towards designing the helicopter to actually go to Mars. And so there's a lot that goes into that, in addition to just being able to fly. The team breakdown, basically AeroVironment was doing what we would kind of consider to be the airframe. All of the main structure of the thing, the servos and motors, the motor drive electronics, not the motor controllers, but and then JPL did essentially everything else. So the guidance, navigation, control, all the simulation, avionics. It's basically what would look like a CubeSat in the bottom of the helicopter that lives in this box down here. And then they did all of the tests, facilities, all of the operational types of things, right, the ConOps for the vehicle.
The big pieces were the rotor blades, the motors, the
The
linkages, the swash plate. We did all those with JPL's inputs on every single thing, but we did all the final detail design and molding and fabrication drawings.
Right. And so our team, I don't think it ever got more than 12 people at a time.
At a time, yeah. It was a small team.
JPL at their largest was 65. And then there were, all of the other NASA centers were involved as well. NASA Ames, Goddard, and Langley, and Lockheed Martin to some degree. So it was a very large team. It was a very large effort. It went on for, at this point now, it's been almost 6 years, I think. And a lot of money. So the total flight time of the helicopter, 90 seconds.
That's what we're
flight,
shooting for.
5 flights.
5. Yeah, which you would
Which is
say,
about
why
it.
even bother?
Right.
But remember that first little rover on Mars, how far did it go? You know.
Yeah.
But then after that, they made the rover that went all over. So we're doing that simple little first step to show it's viable.
Yeah. But dollars per flight second is not very good. So
We had to say that. Your tax dollars at work. Thank you very much.
Okay, so this is going to be a little bit hard to see, but you can come up and look at it afterwards if you need to. The
Look at this pointer I gave.
Oh yeah, there we go. Stand up front. Maybe it'll be easier if I stand up front too. So the general idea for how the helicopter is going to operate is baseline 5 flights, right? Hopefully we get more than that, but hard to say. The first flights are just going to be takeoff, land, show that we can, operate the thing. From there, we're going to start doing, some slight overflights, looking at alternative landing areas, and hopefully by the 5th flight, we can take off, land at a new site, demonstrate that we can hop along behind the rover. But really, this is just a technology demonstration. The value of this thing is to show that helicopters can work on Mars, and we could do a larger vehicle down the line, replace a rover.
Could have an arm. It could pick things up. It could have better cameras. It could map. There's unlimited things. If we can make it.
How large would you envision ultimately?
Yeah. If you get the Saturn V going again, you can do a lot. But with the Atlas V and a rover, if they only sent the helicopter, it could be huge, right? The rover weighs, how much?
That's 1,200 pounds, right?
Yeah. So if we put all that to the helicopter and the entry for that, you could many hundreds of pounds of helicopter unfurling to this, and maybe it's a quadcopter, who knows? But
yeah, they're looking at a next version, which would be around 50 pounds, which that one would carry science instruments.
Would that be with a rover by itself?
That would be by itself.
So this first will just carry imaging.
Yeah, it's got 2 cameras on board. That's about it.
Yeah, one's looking
out at the horizon, one's looking straight down. The straight down camera is being used for navigation.
Wow.
the one in the horizon is just
better
for
because
just
she
capturing.
Okay,
pictures,
go behind again.
Basically marketing.
Yep.
Nice.
Because if you don't do that, what's the point? Like you gotta show people.
Yeah.
Do you have a mission date scheduled?
Yeah. So the launch is July 14th of 2020, and then the landing on Mars is February around 18th of 2021. So it's coming up. It's been 6 years, but now that it's kind of like, ooh, start getting a little pucker factor.
Yeah.
There was once an Aurora project. From an Aurora project. Is this replacing that?
Aurora project.
Is that the name of it or the company?
Yeah, it's, they.
There have been a lot of Mars airplanes. We did a glider concept and made a scale model.
No, it was a winged aircraft. And,
Oh, okay. I don't know. This is all from scratch. Us and JPL. We help from Ames. Wayne Johnson, who wrote the design textbook on helicopters, he was an important consultant during the.
There have been a number of efforts for. So there's Prandtl M as a winged concept. There was a Mars glider early on.
Yeah.
And there was stuff in the 90s as well.
But
so
this has gone the farthest. We have hardware it's on the rover right now.
Didn't you send me a picture where it was being packaged and it was the gold
Yeah.
stuff in the special clean room?
There it is. Yeah.
It's there.
It's on the rover.
Nobody else made it that far.
No, not even close. So it's getting real.
Yeah. Okay, so Matt's already gone through some of this.
No,
but I'll go
just
through it
briefly
again.
go through.
Yeah.
Because you touched on a couple things. I think on this
Environment,
one.
rockets.
Well.
Go through. Okay, I'll go through it again a little. So Matt already touched on the some of the challenges with the environment. Obviously, very cold, but the low temperature or the low density is really what drives the design of the thing.
And a helicopter is good. We can just spin the rotor faster. With an airplane, you got to friggin' book along the ground 10 times faster, and that's not trivial for a tech demonstrator. So this is actually a logical way to do it, even though most people say, "Oh, you were a helicopter first aircraft on another planet."
Right.
But
landing is an issue with an airplane.
yeah.
But the problem with the helicopter, Matt touched on a little bit, the rotors are spinning 10 times faster than they would on Earth relative to the aerodynamic forces. And so typically the way that a helicopter is controlled, right? You tilt the rotor disc and you tilt your thrust vector, and that's how you're controlling your helicopter. On Mars, when you're spinning this thing 10 times faster, the rate that you can process that rotor disc at is much, much lower, right? It's 1/10 for the same aerodynamic forces. In addition to that, the damping due to the atmosphere is also 1/10 lower, and so you have this rotor system that's really slow. It'd be like flying a helicopter, a fly-barless helicopter with the rates turned down to 10% essentially. And so it just
once
is
it gets
absolutely
going, it
uncontrollable.
just wants to stay going.
Right.
Okay.
And
in
you
that
don't have
direction.
enough control authority to pull it back. And so the way that we got around this is to make the whole thing extremely rigid, right? So the rotors are essentially rigidly referenced to each other and to the rest of the airframe.
And they're spun opposite direction,
And they're spun
match
opposite
speed,
direction.
so it's almost canceled out, but there is a little bit of flex, and that little bit of flex means you do have gyroscopic effects. They're really kind of subtle to observe and to describe, but the problems they cause are huge.
Yeah. Right.
And JPL's dealing with that.
Yeah. And so JPL's using essentially the same simulator that they built up to land the previous Mars rover, the Mars Curiosity rover, which had, it was being landed by a rocket crane is what they called the thing, right? So they built a simulator to show how that was going to work, develop a flight control system for that, and they adapted that to use their Mars helicopter. So that's essentially what we were using to design all of the structure for that.
When we say we mean JPL.
Yeah. Okay, let's see. So,
Cover that.
yeah, I covered that. I think you covered all of this. Yeah. Most of the structural requirements actually don't come from flying. They come from rocket launch.
Just like
So-
model airplanes, you're like, for handling it, you got to make it strong enough for crashing. It's like in flight, kind of
Yeah.
like not a big deal.
Yeah.
For this,
In this case, yeah, it's essentially just, strapping this onto the top of the rocket is a very violent thing, right? It's a controlled explosion that you're riding out of the atmosphere.
so,
And so-
don't think about astronauts in a capsule. That's a different rating of allowed shake
Much-
and vibration
much
per
lower.
person.
Yeah. In
This
our
is much
case,
higher.
we have to survive essentially 100 G's for most of the structures in all directions.
Everywhere. Just ran. It's awful.
So that really is what drives the weight of the thing, right? Because you have to design it to survive that, and also all of the interfaces, how you hold on to it. How
But you
attach
want to
to
make
the
it
rotor.
low mass, so you don't have these masses cantilevered out flapping.
Yep.
But you got to make them super stiff. It's a design loop that you got into big time, and at some point you just have to say this is close enough. We're going to accept the risks. And
Right. Right. Another problem, taking anything to Mars, there's a lot of requirements on how clean the whole aircraft or how clean the whole spacecraft has to be, really, and that's especially true on this next rover because the whole goal is look for signatures of life, right? They're trying to find not necessarily actual aliens, but they're looking for carbon footprints and things like that that could indicate that there has been life in the past. And so, for our part, if we drop the helicopter there and they use their really sensitive sampling instruments and they find Matt Keennon or his DNA, right?
No, but listen, my DNA is going because I wound the motors and I didn't use gloves, and it was written off. We coded them afterwards, and they're enclosed. But my DNA is
But everything gets very well cleaned. Everything's baked out essentially, and that's both to reduce the outgassing, what Matt was talking about, oil's going everywhere, and to try to kill off any germs that we could have on there.
So they had to come audit our assembly room, and we'll talk about the clean room later. In their petri dish and counting dust particles, microscope.
Yeah,
Fun stuff.
it's-
Stuff
yeah.
that we've never dealt with at AeroVironment before.
Right. And so the helicopter is strapped onto the belly of the rover, what we call the belly fan. It's riding along beneath the thing, and it's all folded up. The landing gear folds up, and the whole thing is kind of sideways up under the. Yeah, landing gear
And then
folds up
it's
sideways.
on its side with the blades flat and the landing gears here.
Right. And so then when we deploy the thing,
there's a release here, so that lets go, and then the whole thing is cantilevered, just the way I'm holding this. The real thing on Mars is being held by a little fitting at the very top, and guess where all the weight is? Over at the other end. And this is underneath the rover, and then it's servoed down and then dropped. And this is underneath the rover, and then the rover drives away, and hopefully the blades haven't rotated and get caught in the wheels. And he'll talk about this. Wow, it's crazy.
Yeah, so that's the general idea.
But the original concept was this was going to sit in the fender, like wheel well on the side, and the blades, it was going to sit like this, but two of the blades would fold back.
Oh, okay.
And then those had to unfurl and be perfectly stiff and symmetric and balanced.
Yeah,
And
that's
even the executives at JPL said, that doesn't sound viable. Let's try to put you on the bottom.
Yeah.
We wanted to be on the bottom initially, but we didn't. They told us it couldn't. Anyway.
Yeah, and Matt said it started off, looking like some rendering that we had done or AeroVironment had done in 2012 or 2013.
Yeah.
And then it changed and it went through all these cycles and it ended up coming almost exactly back to the original concept. 7 years later. So. Okay, so there were basically 3 full-size vehicles that were built in the last 4 years. There were 2 that we call engineering development models, and then there's what we call the flight model. That's the one that's actually going to Mars. These 2 engineering development models. The first one was just for flight testing.
It's kind of when you do it, kind of just.
Sure.
Yep.
There you go. The first one was basically for flight testing. So this went through what we call system identification tests on force torque sensors and gimbals and all kinds of stuff like that. And then the second one was going through environmental testing, shock, vibration, thermal tests, and that was essentially.
Yeah, the first one was important. So it's a rigid rotor, and you have to know what the precession angle is, right? So when you give it cyclic here, the copter goes up here, and that angle is very important, and you can't always analyze it. It's due to the flexibility of the carbon fiber parts, and also even the gaps in the bearings, the various bearings, and even the stretch and compression of the push rods. It all comes into play.
Right. And one of the big problems in general with this helicopter is that we can't, you can't just put it in the vacuum chamber, go fly it, say, I think I kind of want to change this a little bit, or change it, try it again. Well, we could do it on Earth. The problem is that you can't do that on Mars, right? Yep. So it has to be correct on Mars. We can't test with Mars gravity and Mars atmosphere.
Yep.
And so it all has to be simulated. So we have to show that we can do that. And that's
JPL
what
did
JPL
all the
does.
simulations.
Yeah.
It was super impressive because when they implemented the control laws, they always worked. I mean, they were, and if they, they were so close to being perfect. It's amazing.
Yeah, and then the first time we put the helicopter down,
Compared to our little models, which
right, that didn't work. But the first time we put the helicopter down after they'd done all their simulation, all the tests, just fixed on stands and stuff, they hit go, and it pretty much worked perfectly. Which is what it has to do on Mars.
I think the problems they had were interaction with the gravity offset, which is not even something you have on Mars.
Yeah.
See, we have to pull up on it at the top. You normally want to simulate no gravity by supporting the thing or the person through the center of mass, so you can just go all around. But that would require these huge hoops. And one of those hoops would actually be attached, or one of the arms, and that would change the dynamics.
Yep.
So instead, do it from the top, and it tilts over, it's going to have a restoring force, but it's almost like, well, you tilt over on Mars, you might have wind, so they kind of handled it that way and kind of wrote it off. But it was something, and that's a motorized system, so it does have its own dynamic. So if it interacts with that, it could pogo a little bit and do some funny things.
And they added that into the simulator so they could simulate. Let's see. Okay, so after the engineering development model, we went to the flight model. It's going to be a little hard to see these pictures, but a better version here. Yeah, sure. So overall, or 6 cells.
That's JPL's thing.
That's JPL's. I think we ended up on 5.
Was it fine?
Battery is recharged by a solar panel that's up above the rotor system, so that's what's up here, up top. And it's designed, like I said, 5 90-second flights, and that's only using 20% of the total battery. We're actually using around 65 to 70% just to survive overnight.
There's just no way to do it if you think about it, because it's going to discharge the battery so much overnight. You can't fly first thing in the morning because you're not recharged. And later in the day,
The winds pick up.
the winds pick up, and
So you end up just using very little battery to actually fly.
Yes.
Do you have any plans for like if dust gets on the solar panel or?
The rover has a little deployable whisk broom.
Well, you know, is there like
the thing is the
power
rotor
to spin it up?
Well, it's going to spin up without lift first.
Okay.
So just like on a full-size aerobatic helicopter, you know, spin it up and
Well, so
cross
yeah,
your fingers.
Yeah.
No, we
just
couldn't.
cross your fingers and
We don't have dust on Earth. We literally do not
No,
have it. It doesn't exist here.
Yeah.
You'd think, well, it's just a chemical. We don't have it. We can't put it on there and test it. So we've got some powders that are similar. And and I was literally putting that on the blade and just flinging the blade, and you know, it pretty much goes off.
Okay.
and for the solar panels in particular, they're oversized enough that they'll work at
Yeah.
30% occlusion.
Okay.
Solar panel's about like this size,
Yeah.
Okay.
And the other
and it's
thing is
just
that
sitting on top,
we have a
blocking the
limited,
airflow.
yeah, we have a limited lifespan, right? It's a 60-day operational window from when we drop off the rover to the mission's supposed to be done.
It is not circular, the solar panel.
It's
The
rectangular.
so interesting you ask. On this, the first conceptual CAD model, it was circular. That's one thing we didn't predict.
Right.
But it's rectangular, and that is, it's just the way it's stowed. It's got to be flat under the rover, and we kind of need to maintain a thinness.
Yep.
And so it ended up being a rectangle.
Rectangle. No vibration problems by.
There are.
Yeah.
So that had to be really stiff.
The solar panel's
It's-
like stiffer than the rover blades. It's amazing. You can just, I mean, it's like steel.
But also the interaction between the
Vortex jetting.
vortex generated from the solar
So,
panels to
but
the
it's flown with it in the chamber.
And we have large eddy simulations that NASA did for that, and they gave, the maximum diameter that we could shadow with the solar panel, and so we go right to that.
It's all trade-offs.
Yeah.
Yeah.
I'm just wondering on the solar panels, are they any more efficient on Mars without the atmosphere we have here, or different
That's a good
chemical
Well,
design?
The wavelength is different. I mean, the distribution. I don't know,
Yeah,
the overall
so-
power.
No, the overall efficiency is about the same, 32%, but solar irradiance on Mars is about 2/3 of what it is on Earth.
So it's
And
less.
it's a different spectrum.
So it's less.
So it's
sun straight overhead on Mars, sun straight overhead here, same solar array, you get less power.
Yeah.
That's cool.
Did you say the dust is not abrasive on Mars?
It's abrasive, but it's kind of soft. It's sort of a weird thing where it's like
talcum powder.
yeah.
Well, at least the two simulants that they told me to use for my test, one of them felt exactly like talcum powder, and the other one was a little bit grittier, but it was also very light and very fine. And this is the dust. There's dirt, clumps, there's sand, but it doesn't get blown around. So it's like it's weird with the gravity and the air density.
Yeah.
It's not the same as here.
The dust that blows around and settles onto the spacecraft is pretty soft. The stuff that's hard and heavy just doesn't. There's not enough air density to blow it off the ground. So most of what we're going to have to deal with is about the same hardness as talcum powder. So you can just chew it up in bearings and stuff like that.
But we protect the bearings with kind of like first and second level of protection, but it's not super hermetically sealed. It's just impractical.
Right. Okay. Let's see. So, well, that was
sorry.
an animation. Oh. Okay. So what I'm going to be going over is essentially this, right? We've got what we call the rotor system, which is kind of the two rotor blade servos, motors, solar arrays up top. The landing gear system's down here on the bottom. This is kind of, it's got suspension and damping, try to get the right dynamics for what we need. And then down here on the bottom is an insulated box. This is kind of, this is just to keep all the electronics, all the batteries, everything warm without using too much power, right? So it's essentially the same material that you see on satellites, that goldized plastic film that's wrapped around everything. Similar to that, but it's got an optical coating to try to absorb more solar energy. So getting into some more specifics, rotor blades, I wanted to bring one, but I didn't have room to carry on. These weigh around 30 grams, it's around 1 ounce each, around 22 inches diameter.
And you hold it and hit it with your knuckles, and it sounds like a piece of steel.
Oh.
Right,
It's
very, very high frequency.
very stiff.
Very rigid. Very thin airfoils, 5% thick.
What's a camber?
5%, 4.5%. Pretty thin. This was all, it's machined row cell cores with spread toe carbon fiber and a spar caps, basically the same way we'd make a discus launch glider one, and hard aluminum tooling. So very similar to what we would use for, really any high quality molded composite airplanes.
Would a boron composite serve better? No.
No, not than the real high modulus carbons. It's better stiffness to weight. Yeah. We did look into it though.
Spent a lot of time sourcing and testing the carbon fiber material and the matrix to go with it, because we don't use the regular matrix. It's the epoxy we use here.
Right. It's a cyanate ester system, which is less susceptible to radiation damage and micro cracking and cold.
But it's really a pain to deal with.
Yeah, it
it's
really
very sensitive to
sucks.
moisture. It gets ruined easily.
Yeah.
So they're starting the noontime thing, so we're gonna have to
Is that what's going on?
fight that. But
Okay.
just speak a little louder.
All right. The blades are connected to this hub mechanism, which is one of these. This, again, just molded composites. All of the bearings on the whole helicopter are silicon nitride, so it's a ceramic
bearings.
Oh.
material, very lightweight.
So you can try and bend that. And I mean, it's,
Right, and that's got 72 individual plies in it, so there's
Bend
a
your
lot of
fingers
analysis
before you
went into that
and they didn't
process.
believe we could make that stiff enough, and we couldn't prove it through analysis because it's very hard to model that.
Yeah.
So we originally, the first ones were made out of thin wall titanium, made at JPL, but eventually we convinced them, let us make one, do the tooling, and it was much stronger than even what we thought it would be.
What's that one made out of?
That's carbon fiber.
Nice.
But which kind of?
Yes. Oh, so it's M55J.
Okay.
It's a high modulus Torre.
Yeah.
Might be similar to what you've seen. Yeah. Okay, so swatch plates and servo mechanisms. This is very similar to the normal RC hobby stuff. We'll pass this one around as well. The real one has silicon nitride bearings again, so it's much lighter than this.
So that's titanium part you're holding on to there.
Yeah, so that's all titanium.
I want it back.
The servos are pretty much the same as a hobby servo, except that they have space-rated motors. It's magnetic feedback.
Like Sergio's servos?
Yeah.
Pulse sensor with a
That's
magnet?
definitely the way to go. Yeah, works well.
Brushless.
No, they're brushed.
Yeah, some Maxon motors in Switzerland, some DCX-10s similar to what was used on which other spacecraft? I can't remember.
The
So
drill that just got stuck in Mars.
Oh, was that?
Yeah.
So they were already a design that had gone through NASA to Mars, and we modified it with our gear and our housing. So
Yeah.
that was still a project with Maxon to deal with issues that came up. So, and I was in the middle of that one.
Yeah. What else to say about that? Oh, and the other reason we didn't use brushless, we need really, really high bandwidth control mechanisms, and so developing the brushless controllers for that.
And also the wiring.
Quite a deal.
See, all the controls for the motors, the servo motors, and so the rotor blades are coming out here.
Yeah.
The servos are here. All the smarts are down here. So if you had brushless motors, we would have had the drive signals and the whole commutation signals coming down. I already had 81 wires to manage going through with using brush motors. So brushes,
Yep.
come on guys, give me a break. It's first time, first helicopter, let's go brush. So I'll talk about that later.
Yeah. Okay, and so then once the whole helicopter is built, obviously it goes through quite a bit of testing. And this is all done over JPL. JPL, of course, has it's quite a few test facilities. It goes through shock and vibration testing, so there's essentially just a vibration table that can simulate rocket launch. There's environmental vacuum chambers for thermal overnight testing. And then there was quite a bit of testing on the actual release mechanism that drops the helicopter off the airport, etc. And so here are some pictures of the final helicopter. We might as well just pass this one around.
So there's a good view of the solar array on that one.
Yeah, right. And I'll pass this one around as well. This is just some pictures of the vehicle integration in both the clean rooms at AeroVironment and over at JPL.
Is that swash plate? Who's got the swash plate?
Is that making rounds?
Right here.
It's right here.
Okay, cool. Okay, and then I already talked about flight testing a little bit. There were about 125 different tests on various test setups. We started off just rigidly attaching the helicopter onto a force torque sensor. Then from there we moved on to putting it onto 1-axis gimbal, 2-axis gimbal, and then onto a swinging arm with the gimbal on it, so we could simulate translating flight and forward flight. That all happened at JPL's facility in the vacuum chamber. Might as well pass that around.
Yeah, that's a
I don't
good
think
idea.
anybody
Pass
can
this
see
one.
him. And that's about the end of it. We've got some data on the performance of the system, and then I've got a picture here. So this is from last week. We just did final assembly of the helicopter onto the rover, and so now the rover is going through all of its own environmental testing, and it'll be doing that for the next 6 months. Then we ship down to the Cape, and we go through final launch preparations, and we launch next July. So
Pass it
that's
around.
this one
So
around.
then-
too. That's
Will
pretty
you
simple.
guys be at the Cape when it gets shot off?
Yeah.
Just on the beach with everybody else?
We'll
not gonna-
yeah,
we're not
try. I don't know. We'll try and
How much are tickets?
Yeah, I don't
get
know.
a
You guys don't get to
VIP.
sit in the room when they get the landing and everyone cheers.
We're gonna try.
We'll
But we
probably be
built
there when they fly the helicopter.
So much of it.
Yeah.
Okay, so talk about the motor a little bit. So like I said, Ben did the bulk of the engineering work. I helped, well, there was a team of 5 people that designed the direct drive brushless outrunner motors that are directly connected to the rotor blades and spin the rotor blades. I helped a little bit in the design, but we had specialists, electromagnetics, thermal, mechanical. Ben was on the team. But what I really spent a lot of time working on is how to make the motors and how to actually wind the stators and how to insulate the very sharp lamination stacks, how to test them as you're winding them to make sure you're not stretching the wire and you're increasing the resistance, make sure they're not shorting from wind to wind and from the winding to the stack. I hadn't really done this other than some of you guys just playing with hobby stuff, and so this is the first attempt. I'll pass this around, but it looks horrible. It's I'm trying to figure out how the wire is rectangular and it's a single set of turns. It's very thick wire, and eventually I got it sorted out, and I was able to do this, and it's very tightly packed. You don't see a lot of brushless outrunners where the windings are this tight, but that's what we needed to do to fit on the helicopter to get the height of the motor so thin, get the efficiency, and also get the power, the horsepower out of it, and also not have it overheat. But it's designed for 90-second flights, not 5-minute flights. Even if we had battery, the motor's going to overheat. The motor's designed for 90-second flights, nominally.
Matt, how long did it take you to wind a stator?
The first proper one I did was, I think it was like, was it?
It's 2.5 weeks.
Yeah, it's like 2.5 weeks.
God.
And so I had little pieces that I developed, and built a little machine using hobby parts to actually pull it, but I had to lace each half turn, pull it through, and it's rectangular. So I mean, you can't obviously bend it 90 degrees or 180. And it's these long pieces of wire. You've got to you put it through your fingers, bring it around, and the ends are pointed, but they're polished so that they can't nick anything. And just went through these stages and figured out how to do it and make the joints, because you have to make the connections between the three phases and then the connections going out. Also did the rotor with the magnets. I dealt with that. We had problems bonding the magnets to deal with the temperature. We had to use special materials. The hub of the stator, the part that glues to the inside of this, is a special material we had never heard of, right? I mean, I hadn't heard of it.
Yeah,
Have you
so
ever heard of it?
I'd heard of it. It's called Albumet. It's a 60% beryllium, 40% aluminum metal matrix. So the reason that we used that was for the specific heat capacity.
Let's pass this a little. You can drop it. It's okay.
You
So-
don't want it back?
I like it back. Be careful, they're sharp edges. Don't lick it.
Yeah, so all the waste heat from flight is stored pretty much in the motor.
Yeah, there isn't time for it to go out in 90
Right.
seconds. So we had to, and you can't use aluminum for the hub because there's too much thermal expansion contraction with the temperatures. And the Albumet is like as light as kind of magnesium, but it's kind of like as strong as like 75 or steel.
Yeah, it's
or,
about the same strength as aluminum, and it's about the same stiffness as steel.
and it's super expensive. Super expensive.
And it's toxic to machines.
You don't machine it in your basement.
No.
Well, I was scraping on it. I'm still here.
You're still here?
I'm still here. But you know, it's like, I think it's kind of like solder. You know, solder has the lead in the tin. It's not as bad as just raw lead.
it's a
It's a mess.
Beryllium's
Do the motors cool down faster or slower because of the density of the air?
Slower. Yeah, but there's going to be one flight in a day, and then that's it. It's going to recharge the rest of that day, and probably the next day the motors will cool down eventually through the wiring, through the carbon fiber center mass. So the other thing that I worked on a fair amount is the circuit board. So it uses Hall sensors for commutation because it has to rotate the blade slowly during this deployment phase, and also it's just more reliable to have the Hall sensors. So there's a circuit board in the motor that has sensors and also has the amplifier section of the motor controllers. It's like taking your hobby speed controller, kind of cutting it in half, putting the part that the fat wires go to, putting it with the motor on the back of the motor. But getting that setting on the motor right and getting it clocked right, and getting it glued, and all that was a nightmare. So I'll pass that around.
Filter-oriented control.
Yeah, it is, but in sensitive, so it's a little easier, right?
Yeah. So another thing I worked on a lot was the design of the wire harness and how to fabricate the wire harness, how to install it. So this doesn't look like a helicopter, but this is the bulk of a helicopter. So down here is the box, and then the legs are coming out. There's a rotor blade here. There's linkages going up from these three servos. There's a rotor blade here, and linkages coming up to here. There's a solar array on top. But this is kind of the heart of it. And this centerpiece, we should have brought a mast.
Yeah.
This tube is a stationary tube, and it's carbon fiber, and it's extremely stiff. We have to have it very stiff for the control systems to work properly. But we've got 80 wires coming in the bottom, and then they're coming out 9 different holes. And they're tiny little holes because when I wanted the holes bigger, the mechanical engineer said, you're weakening my carbon tube. I got to make the carbon tube thicker. You can't have the hole that big. So we were going back and forth. You know, I got to get how am I going to make this? So the wire harness is actually all built outside of the helicopter. All the bundles, they're all labeled and they're all twisted. They're all tied up. The power wires and then the signal wires. And I know where they're going to come out. So I have the central heavy wires that go up to the top and the middle, and then the ones that branch out to the servos. They're actually laced onto the bundle, clocked, so they're not crossing.
Is there a reason you didn't use like a digital bus or something to cut down on the number of wires? Or
it just it just wasn't practical, because then we'd have to have these digital chips all over the place that would be freezing to minus 130 every night. So the chips we chose were very simple, like simple gate, simple logic stuff. We couldn't put like microcontrollers out there.
Wiring's just more reliable in the environment.
It's like the brush motor trade-off. It's like, it's what we chose. We kind of knew how to do it. You would see how it goes and rethink next time. But this is how we did it.
What kind of wire and what insulation?
It's just various Teflon, particular non-off gassing. It has to be chemical etch because we had to glue it. But all the wires were laid out and they were twisted and bundled together in sub-bundles and sub-bundles. And then we made these Roacell foam, I don't know what you call them, churros. We call them churros. Hollow churros. Because they had flutes on them because the mass is fluted. And then those were bonded around the wires, and so it was actually a rigid structure of the wire. And then there's loose flying leads out the bottom, and then all these flying leads out the top and then out the sides. And then you say, well, how do you get that in a tube?
Yeah.
So it's like a magic trick. I've designed magic tricks for magicians, weird things. So there used to be a trick, I think, where there's like a tree and the magician does it, and like all of a sudden the branches come out with leaves and stuff.
Oh, yeah.
So it's kind of like that. So we had the tube with the structures on there on a support, and then I had the whole wire harness bundle over here, and then all of these little groups of wires I soldered together with a little loop of beryllium copper, and I put a spectral line, really strong string. And where there were a whole bunch of wires coming out here, I just split this little group into three, so there's 3 strings. And all of those little bundles had to lay down because they need space when you stick it in the bottom. So you see these dark areas, that's where the bundles laid down to insert into the bottom. So all these strings were attached to these pieces over here, and the ends of the strings are run through the carbon very carefully because you can't cross them, and then out the holes. And then those went over to a little disc over here, a plywood disc with rubber bands to keep tension, because I was doing these strings and they can't cross each other. And they thought they just want to cross each other, and it was driving me crazy. So this has to be held perfectly. The harness is over here held perfectly. There's all these little bundles with strings, pulling them through, get them all in. I'm checking it, lights. And this is in the clean room that we set up at AeroVironment. And then you start moving the bundle, or no, we start moving the mast over the bundle, and you start scooting it over 1/8 of an inch at a time. And you're pulling it through, and I've got markers on the strings. If one string gets caught, the mark is going to walk over. And that happened. I had to like back it out and figure out what was going on. Strings are getting caught because there's carbon splinters on the inside. It's
Matt,
manic,
was this
totally
completely
manic.
assembled by you guys, you two? I
The
mean,
wiring,
that thing
I
is
installed
going to
the wiring
Mars. Did
myself.
anybody else work on it other than you two?
There were.
Well, the whole helicopter was assembled by a bunch of people, but I did the wiring. I installed the wiring.
Yeah.
Wound the motors, okay.
I wound them. I was the only one that wound the motors.
The mechanical portion was probably about 5 people.
Okay, so small team doing this.
Yeah. Solving the problems as we went. But anyway, so we scooted it on there, and then eventually each little bundle with this little loop would show up at the hole on the inside of the carbon. So then I was like, pulling it out, teasing it out, and not ripping off that little loop, because then I can't pull on it. And each one was designed to come out at a slightly different time. You didn't want them all poking out at the same time, because then if you had a problem, you pull it back and they all go back in. So I had it all timed by length, and they would come out. And it took me 2 goes on the final flight aircraft, and I pulled it all in, and they all came out, and they weren't chafed. They were, a little bit of chafing, but they had thick Teflon insulation. It was okay. And in the excess length, and then we did all kinds of tests, continuity and shorting tests, and then we cut them to length, and I had a proper solder, do the termination to solder them down. It was very stressful.
How long did it take?
Well, building the harness and pulling it took 2 days. It should have been an afternoon, but it took 2 days because I had trouble, and I was in the friggin' clean room with damn gown and mask and glasses fogging up, and I'm swearing. I got gloves on. You guys can imagine what I was saying.
You
Building
have
the
like a
harnesses.
relaxing
Oh.
playlist or something in the
No,
background.
at some point I did have my laptop running music. But so here's the pictures of the wiring installed, and yeah, here you see the strings and rubber bands up in here, and here's being installed, and here's the harness in the middle, and all the strings are wound to little cardboard cards, getting ready to be installed. I'll send this around in just a second. On the other side of this chart is the clean room we set up at AeroVironment. So like I said, I didn't do a lot of design work, but I did a few important things in setting up our little clean room, which was like, what was it, 12 by 12 feet?
Yeah.
It was pretty small. So we did all the soldering, all the final assembly in this room, and had the petri dishes collecting the dust and the particles, and JPL came and audited it regularly. It was the whole thing.
Did you have a certain class, clean room, so to speak?
They called it a certain level. I don't remember.
ISO 7.5. Whatever that
I
means.
don't know that.
So they keep changing the
Yeah.
number, what they call things.
I'm looking for
It's-
100 or
it's
10,000.
It was
How many
between
particles?
it was between 10,000 and 100,000. Yeah, closer to 10,000.
So this is Ben here, and where else are you on here? Where are my glasses?
1, 2.
Yeah. So Ben Pipenberg's here. I'm over here. This is Viet, and you can just see that the walls of the tent. We bought this clean room prefab thing, and they just stank like chemicals. Like, what the hell did you make this out of? So we couldn't use any of that. So we had to buy. From Uline we bought ESD film, and we made the walls ESD film because they like that stuff at JPL. It's very clean, anti-stat film. So pass this around. Look at both sides. There's craziness on both sides. And then, if you don't mind, I'll just give a little background. AeroVironment was founded way back when, in the 1970s, by Paul McCready, Dr. Paul McCready, human-powered planes. This was the Gossamer Condor. So the prop for this is very similar to the rotors on the Mars helicopter. It's very much inspired by that. Here's another picture of the Helios, the high-altitude solar plane. Oh, so we're building another one of these for SoftBank. It's called the HAPS Mobile Hawk, and that's up at Edwards right now, getting ready to fly.
Hey Matt, somebody asked me, how did Matt get involved with AeroVironment? I didn't have the answer.
How did I get involved with AeroVironment?
Yeah.
Yeah, so that's a cool story.
Yeah.
So I was at Mile Square Park, Fountain Valley, California, in Orange County, and I was meeting up at a model airplane free flight. It was like Flight Masters, with my old junior high school mentor, model airplane builder teacher, Bill Warner. He used to write for Model Builder, Model Aviation, and he was a teacher. He's a cranky old fart, but he really could boil things down, aircraft design, and show you models. And I went back as an adult I was showing him some the toys that I designed. Just hook up with him. And Martin Cowley was there from AeroVironment, who was a senior guy and also a model guy. And he saw me, and I was kind of looking for a job at a toy company. And he said, "Oh, you should work at AeroVironment." I got 0 aerospace. I got 0 engineering degrees. I've got the motivation, enthusiasm, and I build my own stuff. And he said, "Oh, that's fine. I had an architectural degree, and I'm doing drones." So I came in for an interview. I brought all my models. I brought a RC blend. And I flew it around and it dropped little BBs and Falzagos. And Ray Morgan said, "I like the cut of your jib." I think that's good, actually. And pretty much got hired then. But then meet him at a model airplane event, this one, years later, and encouraged him to get into aerospace engineering, and so it's just like the process continues. So it's cool. So anyway, we did the pterodactyl at AeroVironment. It's before my time, but that was a half-scale flying pterodactyl. And then one of my big projects was 2006 to 2011, the Nano Hummingbird. I brought that to Keith that one time, and I think I did a little demo flight. Ben had a lot to do with this when he was an intern, summer intern for 5 summers. And he got us out of a serious pickle with DARPA. We had a milestone. We were building the real one, designing it in the engineer. It was taking a long time. we had a milestone to hit like the next month, and we had to just scab parts together and get something flying to fly 5 minutes. Our longest flight at that point had been like 1 minute, and all I could do is get Ben on it and just scrambled that summer and built this thing, and we got it flying and we hit our milestone, and that allowed us to keep going on the project. So that's about it. Any other questions?
What are you guys doing after the Mars Copter?
Well, we're already on other projects doing interesting things that we can't talk about.
Okay.
You know, our environment's getting more into military stuff and classified stuff. But we want to do more space stuff.
How big is our environment now with people? How many people?
650-ish.
Yeah, and when I heard there were 40 people in the Simi Valley aircraft group in 1996. Okay.
Quick question.
Yes, sir.
You mentioned that if it loses like one of the sensors, it's able to fly with like the IMU. I think it said. Like, what combination of sensors does it normally use?
We didn't talk about what JPL's part is too much, but it's got a visual inertial navigation system. I don't know. I probably shouldn't go into detail. We're not sure what they've cleared for release.
Yep.
Basically, one of the cameras is used to keep track of, how far it's flying over the ground. It's got a LiDAR pointing down to get the height. That's kind of the gist of it. The rest of it is IMU. But the circuit board using the camera is somewhat sensitive to the radiation, and it's got a higher probability of having a problem. If it does have a problem, they can just not use it, and they'll just take off and use the inertia. It might drift around a little bit. It might crash, but should be able to get a flight off with the video navigation computer not working. But yeah, the core of the thing is really cool. It's got the cylindrical lithium batteries kind of in the middle of 5 or 6 cells, and then there's 4 square circuit boards packed in tightly, and then there's wires soldered directly across all the edges of the boards, and there's like no connectors. And then there's a circuit board on top. I think there's one on the bottom too. There's just circuit board, and they're just exquisitely designed and executed. I mean, the conformal coating, the strain relieving, where all the wires come off the boards. And it's interesting. One day I was there, and they were giving out awards, and I was in the technician's lab where all the ladies do the soldering, and they were going out to the main quad area at JPL to get their awards for doing like excellent soldering. It's very impressive.
Will the rover be able to take video of?
Oh yeah, it will. I mean, if they don't do it, that would be silly. It's got to be a safe distance away. It's got to be a safe distance away. So it's not going to be like a close up. And I think the plan is for the helicopter to take video of the rover. I think, but we're not too tightly in the loop with that. That's JPL.
It'll be at least 100 yards away, and it'll be really bad video from the rover.
So yeah, they don't want the helicopter to take off, go out of control, and crash onto the rover, and then dent a lens or cover something up that can't be uncovered. So, the locking mechanism. Can you talk about when it's underneath the rover?
Yeah, sure. So there's a lot of there's the main thing that we have to design for is to not hurt the $1.5 billion national asset. Right, that's the rover. So
it's basically a car.
Yeah.
I mean, it's and we're basically like an indoor model.
Yeah. But when we drop off the rover, we're underneath.
Drop off the copter.
Huh? Drop the copter off the rover.
Yeah.
We're sitting under the rover. And there's some concern that
it's tight.
It's tight between the wheels, right? And so there's some concern that the blades could get into the wheels and jam the whole thing up. And so there are some mechanisms installed here.
The wheels are here. The rotor blades are aligned this way, and you don't want them windmilling. They will windmill. They're direct drive. They very low friction. So he developed a mechanism with a little arm and a little bit of friction, so it'll hold the blades in place with the wind force, but as soon as you drive the motor, it'll pop this little thing out, this little arm that swings up out of the way, and there's absolutely no friction or drag from it at all. And it was a last minute thing they put on us. You got to make this.
Actually, yeah.
And
You can kind of imagine how it works. It's over here. It's a little it's a ball that fits into a D10.
Yeah, we'll pass that around. All these little things, like, oh, by the
There's a
way,
lot of
you
mechanisms.
got to deal with this. You got to, by the way.
Speaking of which, one last question: is that drone registered with the FAA?
It's not. It's tethered. So.
Less than 8 ounces.
So yeah, I don't know if they're going to do a naming contest for the helicopter. Why wouldn't they? You know, the kids are naming the rover already. They should name the helicopter, Spinny or something. Spinny and McSpinface or something.
Yeah, do a Twitter poll.
Call it Benmat.
Benmat, yeah, that'll go.
NASA plans on live streaming the landing.
The landing of the rover itself?
Well, and the takeoff of the copter.
I'm not sure about the copter. The rover, I'm sure.
Yeah. I saw
Anyways,
your thing.
This thing, I don't know. They're kind of trying to keep it low key.
Oh, in case it really failed spectacularly.
Exactly. Yeah. There's a lot of politics involved.
Yeah.
Okay.
I don't know if you be able to answer because it's more in like probably the JPL side. But you mentioned that you couldn't have like a lot of chips everywhere because of the cold.
Yeah.
Did that like influence what they're using to actually run all the flight software? Like,
Sure.
is it?
So
I assume they don't just have like an Arduino in there or something.
No, actually, all of the video processing is on a Snapdragon. If you're familiar with that. The actual control architecture, and this is all public, but there's two automotive grade FPGAs which are not radiation tolerant. They're talking to a microcontroller which is radiation tolerant. And so if one of those goes, those are operating in lockstep, and if one of those FPGAs goes down, it can hot swap over to the other one, and that's deterministic. So it's a radiation tolerant architecture, it's not radiation.
And you said most of the stuff is like simple like logic stuff, so is it like
the stuff that's out
gets
in the cold.
okay, stuff that gets cold is
No,
logic.
my-
So the internal stuff
in
is
the-
still like
yeah.
regular like microprocessors.
Yeah,
Okay.
exactly.
And also just the quantity of stuff that gets cold. We just fewer parts out there to
Heat up again.
to risk failing.
Yeah.
Even if they might be fine. All these trade-offs. I think that's it.
Yeah.
I think it's it.
One last question.
So real quick, these do not do justice to this presentation. All we have is these cheesy little awards, but that was an awesome presentation.
Oh, that's nice. Hey, you got my name spelled right. That's a double score.
Hey, Gordon,
No, I got it.
did you make one for yourself?
No, I did not.
My name
Ah!
So you can turn that off.